Good morning, ladies and jelly beans. This is Mr. Morris again, all the way from Happy Valley Goose Bay. It is November the 14th. It is as of 2:03 p.m. in the afternoon. No baby yet. Patiently waiting. Hopefully you guys and girls found the lesson yesterday very helpful. Again, the same thing with the YouTube, only 15 minutes. We're going to get on the go very quickly. You need pen, paper, pencils. And also you're going to need, you won't need your textbooks right now, but you need pen, paper, and pencils, and we are going to get on to GO right now. So if you need extra minute, just pause me, dink, and then play me when you're ready. Ready? Adotzik, seconds, go. Okay, ladies and jelly beans, welcome to our second installment of our Unit 2. Now, we're going to go over labeling triangles, and what you see in front of you is actually, oh, this is happening again. I love this. There you go. What we have here, ladies and jelly beans, is actually an extension of what we learned yesterday. Labeling triangles. Now, here's what you got. Right here you see we have a good old right triangle. Okay, we have our theta here. And remember, theta just stands for the measure of an angle in a right triangle. That's all it means. So, we labeled our triangle, you'll see here, with respect to where our angle theta is given. So, you know that the side straight across from the angle, ding, 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 ding. Let's use a pretty dotted line. The line, the side straight across here, dun, 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 is always called the opposite side. Very good. The side straight across from the right angle, ta-da, is known as the hypotenuse. And we're left with, last but not least, good old adjacent side. And how do we know that one? It is right next to the angle that we are working with. Remember, labeling right triangles starts with the angle that we're given and that we're asked to work with. So we always start from the angle, get the opposite side, get the hypotenuse, then what's left? The adjacent side. They only stand for the measures of the sides in a right triangle. That's it. Now, make sure you copy this diagram down. Please, mark, get set, go. Should be done. Now, boy. JK. If you need to pause to get this down, please do so. But time is a-ticking, right? So we're going to move on. So that is the first case, or actually the first way we can draw a diagram for a right triangle with an angle given down here, down in the bottom. Now, ladies and jelly beans, let's move on to the second case. Okay, here is the second case. You should notice all that changed from this triangle to this triangle was the position of theta. In the top one, in the top one, we had theta given at the base of the triangle. In the second one, theta is actually given at the top of the triangle. So, how do we label this creature? Same thing. All you do is you simply start from the angle that you're given, this theta. What is theta? We don't know. We don't care at this point. We will learn how to find theta later on. So watch. Simple. Side straight across from theta is always the opposite side. Why? Because it's opposite. The side straight across from the right angle is always the, you got her, hypotenuse, and the side that's left over is the good old adjacent side. Adjacent's kind of left out. Hey, no, boy, no, JK. Now, you will see that later on, to denote, or to stand for this big long word hypotenuse, we don't like that. Guess what we're going to use later on to denote it? We're just going to use this creature right here. We're going to use a good old H. Okay? What are we going to use to denote opposite side? Well, we're going to use a good old lowercase o. And what are we going to use to denote, say, the adjacent side? You got her, a lowercase a. So, what are you going to have for the sides in a right triangle? You're going to have H, O, and A. H for hypotenuse, A for adjacent, O for opposite. Bing, bada bang, bada boom. Done! Alrighty, now, here's something that I want to run over with you as well. How am I doing for time? I think I got 11 minutes left. Here's what we got. We have got to learn how to label our triangles. What I mean by that is, say, let's call this triangle what? What do you want to use? ABC. Easy peasy lemon squeezy. So the vertices are always labeled with uppercase letters, A, B, and C. We always use A, B, C, Y because A, B, C is just the first 3 letters of the alphabet. You could do X, Y, Z. You could do J, K, L. You could do L, O, L prime. Now, boy, you can use whatever you want, right? Point is, if this here is uppercase A, then the side that's opposite is denoted by the letter lowercase a. Okay? Likewise, if this vertex up here is labeled B, the side opposite is labeled small b. Now, if this creature here is labeled C, the side opposite that is, you got her, small c. That's a small c. Okay? Now, confused? Shouldn't be. All this is saying, boys and girlies, don't get it fooled up with H, O, and A, hypotenuse, opposite, and adjacent. We use H, O, and A later on for when we apply trigonometric ratios, okay? All we're doing this for, I'm just showing you this A, B, C, and little a, little b, little c, because this is what mathematicians everywhere use. Now, say if we did the second case, let's do this one as X, big Y, and big Z. Well, X, Y, Z, so you can write it as triangle X, Y, Z. And what do you label this side straight across from this angle? It's going to be, you got her, little x, side straight across here, little y, side straight across here, little z. Now, easy peasy lemon squeezy. If you need to go over this or I'm going too fast, just simply rewind the video and pause. So, I want you to write down this little note. See this? Just like in class, man. Write down this note. Note, when we label our triangles, we may use A, B, and C for the vertices. Then the sides opposite the particular angles we're working with are labeled using lowercase letters A, B, and C, respectively. Okay? So, that is all you're meant to do in this case here. Now, if you need to pause, do so. But, for now, let's go to the next part. You should be writing all this stuff down. I should have said that 5 minutes ago. Nah, boy. I'm sure you are. Okay, let's go. Boom. Next page. Identifying special trig ratios. I alluded to you earlier on in this chapter, in this year, which means I told you earlier that you were going to be working with special ratios, special trig ratios. Now, these are simply values in a right triangle that hold true for any type of right triangle that we have. How do they work? They work by identifying, as you can see down here. I'll highlight it for you in yellow. You have your theta. We'll label your sides. This becomes the opposite, straight down. The one straight across from the right angle is always the H. And what are you left with is A. Okay? Now, here is the first of the special trig ratios, ladies and jelly beans. Very important. Watch, I'm even going to get a marker and write I-M-P. Important. Okay? This is the very first of the trig ratios that you're going to learn about. This, my friends, is tan theta. It is actually known as the tangent ratio. Okay? This is a Greek word, and I don't know what it means. Okay? But I do know that it's very, very important for the study of right triangles. And this particular relationship tells us that the tan or tangent theta of our angle given right here equals the length of the opposite side, the length of this side, divided by the length of the adjacent side. Now, does this hold true for every single right triangle? You betcha. So really we could write this creature as this. The tan of an angle theta must equal the length of the opposite side divided by the length of the adjacent side. That's all it means. That's all we need to know. How does it work? Simply put, ladies and gentlemen, no matter how you draw your triangles, whatever your right triangle is, your angle at the base, the length of the opposite side to that angle, divided by the length of the adjacent side, will always give you whatever the tan of the angle is, this theta right here. Okay? So say if this was tan 30 equal to number, well, it equals a number, duh. Good way to go, Morse. Equals some number, then you can be rest assured that the length of this opposite side divided by the length of the adjacent side will be equal to the tan of whatever angle this is right here. Okay? Does it work? Always and forever. A little bit later on, you'll see where it comes from, probably in next year. But for now, what we do, we simply introduce these special formulas. So remember, it's the tan of theta equals the length of the opposite side divided by the length of the adjacent side. In your calculators, they are programmed with all these special values. You can take the tan of, say, this angle here. It might be the tan of 50 degrees. It might be the tan of 38. It might be the tan of 2. Point is, there's always a value right there, okay, for the tan of an angle equal to the opposite side divided by the adjacent side. So, here's another way to look at it, just another diagram for you guys and girls. We got the tan of theta, the tan of this angle theta right here. Whatever this angle is, tan of 20, is equal to the length of the opposite side, which is this one here, divided by, this line means divided by, the length of the adjacent side down here. Does this always work? Yes, I guarantee it, 550,000%. So, what can we use this creature here for? What can we use this tan theta for? Well, let me tell you, ladies and jelly beans, you can use this for almost any kind of problem involving right triangles. As long as we're given an angle and the length of the opposite or adjacent sides, we can find, depending on what we're asked, lengths of sides in triangles and the values for theta, or the values for an angle in a right triangle. Now, how is this? Easy peasy lemon squeezy? Good. Fantastic. Now, give me a second. I got to pause this. And, ladies and gentlemen, okay, I finally found what I need to go. I was gone for about 5 minutes there, so anyhow, watch. Here's what I want you to try right now. I want you to try to do these two questions. In triangle ABC, where angle C is 90, the hypotenuse is 13 centimeters, and the side opposite to angle A is 12 centimeters. What is the length of the side adjacent to angle A? What is the length of the side opposite to angle B? Sketch the triangle. See if you can figure these out together. Also, I want you to try number 2. Draw to scale a right triangle where tan theta equals 0.25. So that means what you're going to have to do is come up with two side lengths where the opposite side divided by the adjacent side has to equal what? Should be 0.25. Why? Because it says draw the scale in a right triangle where the tan of theta equals 0.25. What theta are you going to use? Well, if you got a right triangle like this, say if you use this angle here as theta, you know this side is opposite, this is adjacent, so make sure that the length of this one divided by the length of this one equals 0.25. Draw it out, make sure it's a right triangle. I got compass sets and stuff there. Take your time. Then I want you to use your protractors and measure these angles right here. Measure the angle from which you're starting at, say if it's right here, then measure the other one. And you're going to notice that no matter what the lengths are here of the opposite and adjacent sides, as long as this ratio of 0.25 is kept, these thetas, this theta right here should be a connection there between, say, everybody's triangle, right? So I want everyone to try these two. What you can do now is you can just keep this up, pause it. We are out of time here now, so this is Mr. Moores signing off. Take her easy later, Gators. If you get done before the period is over, please review Unit 1. Later.